Hello everyone, welcome to our channel Mathematics Parshala. This is a problem of CSIR NET December 2023 Mathematical Sciences. This is a problem of linear algebra part C. The question ID is 704076. So first we read the question. Suppose a 7 by 7 block diagonal complex matrix A has blocks this. 4 blocks are given along the diagonal. Then which of the following statements are true? So for this we know the characteristic polynomial of a matrix is equal to the product of these blocks. So first we write the characteristic polynomial. We denote the characteristic polynomial of A by chi A x. That will be the characteristic polynomial, the product of the characteristic polynomial of these blocks. So first this is a block of size 1. So 0 will be an eigenvalue. So this is x minus 0. So this is x. Then this is 1, a block of size 1. So x into x minus 1. The characteristic polynomial will be like this for these two blocks. Then this is a block of size 2, and again 0 is eigenvalue. So for this the characteristic polynomial will be x square, x minus 0 whole square, that is x square. And finally for this 3 block of size 3, 2 pi I is eigenvalue and 3 times, so it is x minus 2 pi I whole to the power 3. Now we get this is x cube, x minus 1 into x minus 2 pi I whole to the power 3. So this is the characteristic polynomial of A. See, the eigenvalues are 0, 1 and 2 pi I. These are the eigenvalues of A. The algebraic multiplicity of 0 is here. Algebraic multiplicity of 0 is 3. Algebraic multiplicity of 1 is 1. And the algebraic multiplicity of 2 pi I is 3. Now, look at the option. The characteristic polynomial of A is this. So, we find that this is the characteristic polynomial of A. So, option 1 is the correct option. Then, look at option 2. See here, we have to find the minimal polynomial of A. So, first see, in this matrix A will be like this, 7 by 7 matrix. The blocks are here like this, 1, this is 0, 1, 0, 0, and then finally this 3 by 3 matrix. So now, see here, for 0, for the eigenvalue lambda equal to 0, what is the size of the largest block corresponding to this eigenvalue? What is the size of the largest block corresponding to this eigenvalue? See here, there are 2 blocks corresponding to 0, and the size of the largest block corresponding to 0 is 2. This is so we know that the size of the largest block, if when lambda is an eigenvalue of A, then the size of the largest block corresponding to this eigenvalue lambda is equal to the multiplicity of a multiplicity of the root in minimal polynomial. So since the size of the largest block is 2, so in minimal polynomial of A, that is we denote it by max. So here this 0 appears 2 times. Number of appearance as a root, as a multiplicity, the multiplicity as a root in minimal polynomial is equal to the size of the largest block corresponding to that eigenvalue. So since it is 2, so x square appears as a root, x square appears as a factor in minimal polynomial. Then consider lambda equal to 1. So here algebraic multiplicity is 1. So it is it will be just x minus 1. 1 appears in minimal polynomial 1 times as a root. And then consider this 2 pi I, lambda equal to 2 pi I. See, there is a block corresponding to this 2 pi I of size 3. So this 2 pi I appears 3 times as a root in minimal polynomial. So it will be x minus 2 pi I whole to the power 3. Actually, to find this, we need to know that result, that the size of the largest block corresponding to a eigenvalue is equal to the number of appearance as a root in minimal polynomial, nothing else. So this is the required minimal polynomial of A. So look at option 2. This is true. So we find that this is the minimal polynomial of A. So option 2 is the correct option. Oh, actually, there is a mistake. Sorry. See here, for 2 pi I, this is not a block of size 3, because if this is a block of size 3, then this super diagonal position, this 0 should be 1. So this is actually two blocks, one of size 2 and one of size 1. So this is actually corresponding to 2 pi I. There are two blocks here. One is this and the other is single just 2 pi I. Okay. So the size of the largest block for 2 pi I is actually 2 here. Sorry. So this is not 3. So 2 pi I will appear 2 times as a root in minimal polynomial. So this will be 2. This will be 2. So this will be the minimal polynomial of A. But in question there is given that x minus 2 pi I whole to the power 3 is a factor of minimal polynomials, which is not true. So option 2 is not the correct option. Okay, so the characteristic polynomial and the minimal polynomials of A have been studied now. Then we come to the option 3 and 4. This is about the dimension of the eigenspaces corresponding to the eigenvalues of A. That is actually related to geometric multiplicity. So now also there is a result that we know, that the geometric multiplicity of an eigenvalue of A is equal to the number of blocks Jordan blocks corresponding to that eigenvalue, here written lambda, corresponding to lambda. So there are total number of blocks corresponding to lambda is equal to the geometric multiplicity of lambda, and geometric multiplicity of lambda is actually equal to the dimension of the eigenspace corresponding to lambda. So we find that actually the dimension of the eigenspace equal to the number of blocks corresponding to an eigenvalue. So first consider lambda equal to 0, the eigenvalue 0. So there are, see how much block is there corresponding to 0. This is a block of size 1 and this is a block of size 2. So there are two blocks. Corresponding to 0. So the dimension of the eigenspace, that is the geometric multiplicity of 0, that is the geometric multiplicity of 0 is equal to 2. Then consider lambda equal to 1. Algebraic multiplicity is 1, so geometric multiplicity of 1 must be 1 because it is less than equal to algebraic multiplicity, and since lambda is a root, so geometric multiplicity, lambda is an eigenvalue, so geometric multiplicity must be at least 1. Then consider lambda equal to 2 pi I. See how many blocks corresponding to this 2 pi I. Just I said that from this 3 by 3 matrix, it is given that there are two blocks. The one block is of size 2 and one block is of size 1. So there is two blocks. So geometric multiplicity of 2 pi I is actually 2. So geometric multiplicity of 2 pi I is equal to 2. So the dimension of the eigenspaces corresponding to the eigenvalues 0, 1, 2 pi I are equal to, we got for 0 it is 2, dimension of the eigenspace, that is geometric multiplicity. For 1 it is 1, and for 2 pi I it is 2. So see that option 4 is the correct option, 2, 1, 2. So option 4 is the correct option, but option 3 says that dimension of the eigenspace of 2 pi I is 3, which is not correct. So option 3 is not the true option. So here 1 and 4 are the correct options and 2 and 3 are not the correct options. So this is the solution of this problem.